Hello, everybody. I'm Gang Tao. I'm the CTO and co-founder of Timeplus. Thanks for the solars. I'm going to have an introduction about Edge AI. How can we do the anomaly detection using the large language model? First, something about the background. The edge environment, are generating large amount of data. So that means there need to have a good way to detect those anomalies and ensure the performance, right? But the challenge is that the traditional cloud-based solutions often has some limitation, like the latency, because for the edge network or IoT network, the network is not so good, so it's usually hard to have a good latency when you're connecting to the cloud services. And it's hard to scale locally when you have large volume, fast changing streaming data, right? And last, it's also very not cost effective. Uh, other thing like security is also a concern. Sometimes you want to make your data private to yourself. You don't want to upload your sensitive data to the network. That's why for this kind of real-time edge-based anomaly detection or data processing, you want to keep everything locally. That's the topic I'm going to talk today. So here's the edge AI solution overview. You can see locally on the edge. So you have your sensor, you have whatever the data is coming, you're processing those data locally, and you actually can leverage local large language model to process those data. So at the same time, you actually can upload the processed data to the cloud as well later if you really want to do some more sophisticated data processing. You actually can do that as well. But today, I'm going to focus on the edge, how we can do some local anomaly detection on the edge. One thing about Ollama, so Ollama is actually the model serving component. It's open source, so it can help you to run different model locally. It provides an OpenAI compatible API, and it does support different platforms. Like in my case, I'm running macOS with M2 CPU, GPU. Actually, Ollama support is as well. Lastly, you can do some model customization as well. Okay, so as today's topic is about using LLM, right? So I'm going to talk about why the real-time context is relevant here, right? So for example, I have an example here. So when you try to ask LLM to do some task, in this case, I asked LLM to do some recommendation for me, right? Which is a typical machine learning job, like real-time recommendations. But in my case, I asked the question, so what's the recommendation for my trip today? But unfortunately, there's no good ways to answer these questions because there's lack of real-time context. For example, the ChatGPT asked me, what's your interest in, what's your location, what's the weather, and available time, something like that. Actually, these are the real-time context. Here you can see I revised my question to LLM, say, I'm visiting Tokyo today. Today is rainy, and I have 2 days plan, and I like more like nature landscapes over the historical landmarks. So and then actually you can see that large language model can make a good recommendations based on this real-time data, right? So that's why providing real-time, high quality, and relevant context to large language model can make it do a better job, right? That's also similar in any any data context, like you have like in IoT or edge case, you have a large number of data. You actually can leverage this data to enrich your RM task to make it provide a real-time context. So that's why you need generally you need such kind of tools to help you, right? So in today's time, I'm going to show how we can leverage Timeplus as a real-time context builder to support this RM to do a better job. Like I mentioned, with these real-time data, So it can fill some gap that large language lacks. First is the data freshness, like because large language model are usually trained on some static data set. So it doesn't have those real-time data or private data, right? So you can actually leverage these tools to help you to build more fresh data as context. Also, you need more distributed data source, like data is coming from different places. You want to merge them together, transform, and provide a good data to your large language model, like traditional data integration job. And also the like short memory, like a large language model usually has a very short context window, right? So with these data tools, these real-time data processing tools, actually it looks more like a database, provide you the more relevant context. Last is like a quality issue, data quality issue, privacy issue. All this stuff can be handled by your data processor, right? So this is a quick architecture. It's an architecture about the time plus. It actually you can think it as a like a database plus streaming processing, right? So when you have different data, like your event data is coming from like HTTP or like other push to the through the SDK. So all this streaming data is going into the Timeplus, and Timeplus will store it and process it in real time in a real time manner, and send data to some downstream stuff, right? And you can interactively query your stream data or analysis your stream data using SQL. And Templus is actually built on top of this the open source database called Proton. There's a GitHub project, can take a look. So here is how in today's demo, I'm going to demo how we build an LM agent to do the anomaly detection. So this is how we build this solution, right? So fundamentally, in the real time, you have your event data stream or data source, and you can send those data to an event stream like Kafka or Nets or whatever, or you can directly push to the time path or whatever. So then here we have a streaming of data, and user can run a query on this streaming data. User query through SQL, right? User run this SQL query on the events you have. It's a real-time query. That means as soon when you have some new data, right, new events, actually it can be processed by this query in real time. And at the same time, actually, the query is talking to the internal agent, the large language model agent, and this agent will build a prompt. And this prompt actually also came from the data because usually those contexts can be retrieved from data, right? So we use this data to build a prompt, and the agent will send the inference request to the large language model and then come back. But overall, for the user's perspective, the user only need to run the query. So everything is done on query. So this can greatly simplify how user interact with large language model. I will show the demo later. So, and today I'm going to show you a case study about the DDoS attack in the IoT system, right? So the DDoS is a distributed denial of service attack. It has become a major concern in the context of the IoT network. So globally, there are actually more than 16 billion devices today. So it's a large number. And usually there's weak security and lack of standard that means a lot of these IoT devices are vulnerable to these kind of attack. And there's urgent need for IoT security services, so we can have this kind of DDoS attack detector to help protect our system. So I have a picture here. It's actually generated by the OpenAI. Okay, So in the DDoS case, actually, traditionally, there will be traditional machine learning algorithm. You can do uh, the DDoS attack detector. Fundamentally, it's actually a classification problem, right? Any such kind of anomaly, you can think it's a classification problem. You can use like a statistical model, like a mean value or z-score. You can also use some machine learning model like a SVM or KNN to do this kind of classification. Or there's a time series model or deep learning model, right? These are all the traditional machine learning model. But today, what I'm going to show is actually uh, how we can leverage large language model to do that, right? So in our case, we reference this paper, the application of large language model to DDoS attack. Uh, in this paper, actually, it leveraged a method called few shot promoting. That means it's a few shot learning. We just provide a large language model some sample of the labeled data of labeled DDoS or not DDoS, right? And then we construct the prompt using like 20 sample from this data set. And we also select part of the features from this data set, like 5 of these features, and ask the large language model to help us to identify whether an event coming is DDoS or not. So this is the data set. I'm going to show you. So this data set came from the IDS 2017. So it actually contains like 85 features and with label of benign or DDoS. And user can just, I've already uploaded this data set to the S3. So user can just run this SQL to actually insert the data. So I'm going to do a quick demo about how this data looks like. Okay, so I'm going to the data console. The SQL console, we have network traffic. So this is actually the imported data set. It's actually a static data. So since there's no new data, because I just imported data using the CSV, but user can query this data. We can see what data looks like. I run this SQL. You can see there's an ID, it's incremental ID, and there's a 85 features as following. There's a lot of features. And at last, there's a label, say whether this data is a tag or not a tag, right? So that's our data set. Let me go back. Okay, so we now we have this data set. How can we leverage this data set to build a DDoS detector? So actually, we leverage this few shot prompt, like I mentioned, and this prompt contains several parts. The first part is the system prompt. So we ask you will be provided with a sample of network traffic data, and that is split between training data and a single test data, separated by those symbols. Each row of data is separated by a new line, and each row has features separated by type symbol, and use this information from this training data to predict the test label, whether it's benign or DDoS for the testing data. First, explain the reasoning, and then indicate the predicted label using this at symbols. So that is system prompt. This system prompt guide the large language model to do something. And these are actually the real-time context. We actually use a template. It's a Ninja template, right? This part is actually the samples, right? The training data. So we select 5 features like this packet length, minimal packet length, STD of the packet length, average packet size, flow duration, and IAT-STD, right? These are all the data coming from this query called actually using this query, we can randomly select 10 samples from all the data set. And last, we provide the real-time data. These come from the test data. This come from your event of network. So we put so with this prompt, we actually ask large language model to run a classification using this sample data and to detect whether this new coming event is a DDoS or not. Right? Let's run this sample a little bit. And copy this query to my SQL console. If we run this, you can see actually we randomly return 10 records. Some of them are labeled DDoS, some of them are labeled as benign. So, and there are 5 features we are going to use to build our prediction. Okay. That's the template, and we actually can. Let me first try this template. Okay, let's go to the agent builder. Actually, you can see this is the agent build UI. We actually create this agent called the DDoS, and we provide the prompt template as this. And you actually can just evaluate this template. We are not sending this to the ARM yet, but we can evaluate. Say I have some features like this. I run a few. I fill some test data here, and we actually can run this evaluate this feature, and we also can run a one-shot one. Okay, let's go back to the slides. So first, to run this demo, I need a test stream, which is an event that continuously run my test, right? So this is how we can simulate such kind of event. So we actually leverage the tool called the random stream. So I've already created a random stream. The random stream is just a continuously updating event that give you just one field called ID, because my data has like this number, total is this number. So this stream actually randomly select one of the event ID, and then I will join this stream join a table. That means we randomly pick one record from this whole data set. So if we run this, we actually can see how this random stream is. That's your simulation of the real stream. Let me run it. You can see actually this is the first one. Because it's a 10 second, it's a EPS is a 0.1. That means every 10 second, I will generate one, I will randomly choose one record from my test data set. And using this stream, I actually can test my large language model, my agent, whether it's working and what's the result, right? So let me go back to my slides. Okay, so with this test stream, it's something like a event-driven stream, right? There's new event coming. I send this new event to my agent, which will evaluate the prompt and send the prompt to the large language model, right? So, and this is my detection SQL, what the SQL looks like, right? So we just select all the features here. Like I mentioned, we have 5 features, and then we have the ground truth is the label, and we construct these 5 features into a map. So that's because we want to generalize the agent call, right? For each agent, some prediction, some task may need fewer features, some may need more features. But in this case, we just put a map here, and then we send this data, say, call the agent. The agent will evaluate the prompt, and then the last work is actually we need to extract the data, extract whether the large language model think it's a DDoS or not. So that's our detection SQL. Let's run this. Let me go back to the agent. Now I'm using Ollama local model, but I'm going to first show the more powerful model. Like I'm going to use maybe the GPT 4.0. Let me see which one we want to use, or maybe we start with GPT 3.1, 3.5. So and then we run this new SQL. So this is the SQL we are going to run, right? So these are features, labels, in map feature into the large language model. We call the agent, and the response here we extract the information. Let's run this. So now we actually simulate this test. We can call it an experiment. We actually construct this and send data to the GPT 3.5. You can see actually this data labeled DDoS and the prediction is DDoS as well. There's new data coming. This one is wrong because the ground truth is DDoS, and language model think it's not. But we can take a look how it works. You can see here is actually the evaluate input, right? This is output. This is how the large language model return. This part is reasoning, and it gives some predict label, right? So, okay, let's stop here. This is the demo how the large language model works. Let's continue. So this is the response. I'm using one of the model, like Llama 3.2. It's hosted by the Grok. You can see a part of this is the reasoning, like I just showed, and part is the final one is the DDoS, is the prediction made by the large language model. So what if we use some, like I mentioned, what if we use some local model, right? So, because like I mentioned, on the cloud, we can use GPT-4. And what if I'm just using my local model, say Ollama? I want to use my local Ollama, like 1B, Llama 3.2 1B. It is the latest model, and has fewer parameters. That makes it easy to run because it doesn't require so many resources. Okay, and let's run this query again, the same query, but we have switched agent. Now it's using the local Ollama. Let's run this. Now actually, I'm running this SQL purely locally. The Timeplus is running locally, and Ollama is run locally. You can see, this time it make the prediction right. But sometimes sometimes the local model cannot make a good prediction. Like this one is good. And let's see, is there other? Yeah, but some others you can see the local llama make one good prediction, but it's not consistent, right? For this one, if you take a look at the prediction, it doesn't follow the others, right? It didn't give the prediction in a formatted way like other sophisticated model, right? And so that's why I think local model we can run it, but local model is not designed for some sophisticated jobs, right? So we do have some performance monitoring. So this is some performance monitoring I did on different model. You can see that GPT-4o has a very good performance because we have all the data. You actually can just run a query in Timeplus to generate all this performance report. Like you can see the Llama 2 3.2 1B model. It's very low because most of the labels prediction didn't follow the order. But some other local models can do the job, but not very well because this is like a binary classification. If your performance, you have to be the position has to be higher than 50% means that the model knows something, right? GPT-4o is very good because considering in this case, we didn't train any data. We didn't pre-train the model. The model is a generic model, right? The only learning is actually we call the in-context learning. It fully depends on those samples we provide to the large language model in the real time, right? So that means like 80% is already a very good job. Let me show you actually can run this in Timeplus. You have this model performance monitor. This is my past test, like GB4 is like much better, do a much better job. Okay. And also with Timeplus, I also log all the RM call. So all the call are logged, and I monitor how's the local latency, like we call different large language model for some specific tasks, and what's the average or P90 response time, right? So some models like this one, Mistral, Nemo, is super slow locally, and some models is fast, like this 3.2 1B is better because this is a smaller model, right? GPT-4o is okay. It's even it's on the cloud, but GPT OpenAI provide a good facility for you to hosting those inference architecture. So last, as our topic today is about how we can run local large language model for this event-based anomaly detection, right? So we can see local model can run, but still has some limitations, not the best format. So there are some technologies that can help us to optimize the performance, the local inference performance. First is quantization. You actually just convert the model weights from like a floating point, like a 32-bit, to some lower precision, like NT8, right? That's the quantization. And as distillation, that seems similar, like you have a large model, has very good knowledge, but you want to transfer those knowledge to a small model, right? Like the teacher-student model, you train a local model that has a specific knowledge, or you can do some other like proning stuff. But I believe with the fast development of the large language model, running powerful local model will be not hard, will be easier and easier in the future. Okay, that's all my presentations. There's some takeaways. So the edge computing with local large language model can provide you operational efficiency because you don't have to have external dependency, everything running locally. It's easy to run, but the capability of the model is not best, but I believe it will be better and better, right? And by providing real-time and historical data context, your your large language model can do a better job. Like I mentioned, in our case, we actually provide the sampling you can see the sampling is a context, and that's from the historical data, and the real data is from your data streaming, right? That's how we demo this anomaly detection works. And last, I think those kind of streaming processing platforms such as Timeplus, you can see actually it's super easy to use. You don't have to write any lines of code. Everything is done in agent. That's a SQL, right? You just construct your prompt, and then you can run the SQL to do the anomaly detection. Okay, thank you. That's all I'm going to share today. Thank you very much.